As we know from second law of the thermodynamics, Kelvin Planck's statement of second law of thermodynamics, that heat always flows from body at a higher temperature to body at a lower temperature. Okay, I have shared here a white screen. Now let me tell you how heat flows. Let's say it is source at temperature T1. Then a heat engine has been heat flows in direction. Then it is steam at temperature. So heat follows from source to sink. Here we know that we can get work output W. So it is the basic principle of heat flow. So source, then let me write it E, that is the heat engine, and then the sink will be at temperature T2. The work will be. You know the deficiencies is work done by service. This will be the efficiency. So the example of conduction, convection, and radiation can be both shown by this picture. Conduction means roughly where the heat flows inside the solid. Convection, there fluid flow is required. Radiation, as we know that for radiation heat flow, no medium is required. It can be it can flow without a medium. Here in radiation, how it travels through empty space. Radiation is where heat travels through empty space. And for convection, liquid and gases, and for conduction, it is inside the solids. So there are the three modes of heat transfer: conduction, convection, and radiation. Now, what is the difference between heat and temperature? Temperature is a measure of the amount of energy. It is the amount of energy possessed by the molecules of a substance. It is a temperature. It manifests itself as a degree of hotness and can used to predict the direction of heat transfer. As we know from the second law of thermodynamics, that heat can flow from body at a higher temperature to body at lower temperature. So only temperature decides from which body to which body the heat will flow. That is, it always flows from body at a higher temperature to body at lower temperature. So by means of temperature, we can know heat will flow in which direction. And heat, on the other hand, is the energy transit. Spontaneously, heat flows from a hotter body to a colder body. So usual symbol for heat is Q, and common unit for measuring heat are joule and calorie. Also, heat transfer tells us how and with what modes the human heat is being transferred, and what rate, and secondly, at what rate the DQ is transferred, the heat is transferred, and temperature distribution in the body. So by reading heat transfer, we can know how heat is being transferred, heat flow. This is the DQ means temperature difference. At what rate temperature difference is transferred, and temperature distribution inside the body. Now there are, as we have already discussed, there are three modes of heat transfer: conduction, second one is convection, and third one is radiation. Firstly, let us start with the convection in details. Now, and the energy transfer across the system boundary due to temperature difference by the mechanism of intermolecular interactions. We know that the solid contents of molecules. Now, when the heat is being given to some part of the molecule that will be heated, and the heat will be transferred from molecules at higher temperature to the molecules at lower temperature. So conduction obviously need matter. Obviously, without the matter, there will be no conduction. This is the basic fund of the fundamentals, and does not require bulk motion of the matter. Bulk motion of the matter will be required in convection, not in conduction. So in conduction, heat will always flow through the body by means of intermolecular interactions. Now, firstly, we have to know what is Fourier laws of heat conduction. The rate of heat flow through a simple homogeneous solid is directly proportional to the area of the section at right angles. Let us say it is the area at right angles. It is A in the direction of the heat flow. The changing temperature. Let us say at the hotter end it is T1, the cold end is T2. Change in temperature is T1 minus T2 with respect to the length. So Q is directly proportional to area multiplied by change in temperature in direction to the heat flow. X direction it flows in the direction of x, change in temperature at the direction of x. So Q is directly proportional to A into dt dx. So Q and the Q varies as A dt dx. So the proportionality constant has been added, that is K. Okay, now for heat conduction, let us say a wall is there. It's a wall. Okay. No. This is the direction of the heat flow. Let us say this is at temperature T1, and the right face is at temperature T2. And the direction of heat flow is x. It is flow from the direction x. Excellent. So the Fourier law of heat conduction Q is directly proportional to area dt with dx. And if we have to add proportionality constant minus k dt dx. This is the Fourier law of heat conduction. So Q is minus K dt dx. Q is the rate of heat flow through a body per unit time. Watt. And K, proportionality constant, it is also called thermal conductivity. It is watt per meter degree Kelvin. How it comes, we will know. And A is the cross-sectional area in the direction of heat flow. That is here. This cross-sectional area in the direction or the perpendicular direction of the heat flow. And dt, gradient of temperature, Kelvin per meter. In I direction, del T del x. In J direction, del T del y. And in K direction, it is del T del z. So if we add del T del x, del T del y, and del T del z, total dt will be obtained. So Q in x direction is Kx when the heat flow is in the x direction. And circular coordinates also R. Now, how the concept of thermal resistance come from the Fourier law of heat conduction. When two physical systems are described by similar equations and have similar boundary conditions, they are said to be analogous. Now, the heat transfer processes may be compared by analogy to the flow of electricity as electrical resistance. So, heat transfer are being compared with the electrical resistance. Okay? Now, we know from Ohm's law, current is equal to potential difference divided by electrical difference. By the same, if we apply the same analogy in the Fourier equation, that will be changed to, so current is analogous to heat flow rate, I is analogous to Q, and potential difference is for current is temperature difference for heat, and electrical resistance is dx by k. How it comes, we will know. Now, by comparing equations, we find this I is analogous to Q, I is analogous to Q, dV is analogous to dt, and R is analogous to dx by k. The quantity dx by k, that quantity is called thermal conduction resistance or thermal conduction or THCO. Next. Okay. So it is being shown, the heat is being shown, heat flow is shown by a circuit. So one end temperature is T1, heat flow Q, another end temperature is T2. So resistance is dx by Ka. Resistance is dx by Ka. See, from this equation, that equation can be changed to this. So dt by dx by K. Now if we change this equation, now so this equation, what will be there? Q dt, keep dt over here, dx by k, dx by k. So dx by k will be the electrical resistance analogous to electrical resistance. Dx by k is analogous to electrical resistance. Dx by k. The reciprocal of the thermal resistance is called thermal conductance. The reciprocal of that thermal resistance dx by k is called thermal conductance. Reciprocal means k by dx, that will be thermal conductance. It may be noted there. Okay. Now convection. An energy transfer across the system boundary due to temperature difference by the combined mechanisms. So in convection, there will be combined mechanisms of intermolecular interactions and bulk transport. So some fluid flow is required here. For convection, for conduction, no fluid flow is required. It is the flow inside the solid, but for convection, there must be some fluid flow. And from the Newton law of cooling, from the Newton Q, heat transfer by convection is HA, TS is the solid temperature, and TF is the fluid temperature. That's how heat transfer through convection can be obtained. Now, a electrical circuit analogous to electrical circuit has been shown. So resistance here will be 1 by HA as temperature difference divided by the term, that is HA. So 1 by HA will be there. If we change the equation like that, like here, like that, so dt by that one, so the equation will become, the resistance will become 1 by HA. So from Newton law of cooling, Q is the rate of convective heat transfer. What unit will be what? Heat transfer coefficient, H is the proportionality constant. It is called heat transfer coefficient, which is not a thermodynamic property of the material, but may depend on the geometry of surface, flow characteristics, thermodynamic properties of the fluid, etc. Its unit will be watt per meter square Kelvin. So K has got the unit. Let us go back to that. What was the unit of K? Watt per meter Kelvin. And for unit of H, watt per meter square Kelvin. S is the surface area exposed to the heat transfer from which convection is occurring. It is meter square. And Ts minus Tf. Ts is the solid temperature body, temperature solid body, and Tf is the fluid temperature. So temperature difference between surface and the coolant. This is the temperature difference between surface and the coolant, and unit Kelvin. Now some values of heat transfer coefficient. You need to have already learned that watt per meter square degree Kelvin. For gases 2 to 25, liquid 50 to 100. For forced convection, it is 25 to 150, 50 to 20,000. And for boiling condensation, 100 to 1,500 to 1 lakh. Now let us come to the radiation. Radiation heat transfer involves the transfer of heat by electromagnetic radiation. That is, no medium will be required. Heat will be transferred by electromagnetic radiation only, and that arises due to temperature of the body. Like between Earth and Sun, there is no medium, but there is a temperature difference between two bodies. So if Earth is taken as sink and the Sun is taken as source, so heat will flow from source to sink, from higher to lower temperature. So radiation does not need matter. We know that between Earth and Sun there is no matter. Now, some laws are there that govern radiative heat transfer. First, Owen's law. It states that the wavelength corresponding to the maximum energy, is inversely proportional to the absolute temperature of the body. So, lambda n directly proportional to the 1 by T, and lambda n into T is equal to constant. So, the wavelength is the inversely proportional to the absolute temperature of the body. Now, Kirchhoff's law. It states that the emissivity of the body at a particular temperature is numerically equal to its absorptivity for radiant energy from body at the same temperature. The emissivity of a body at a particular temperature is numerically equal to its absorptivity. So, emissivity is equal to the absorptivity for radiant energy body at same temperature. This is the Kirchhoff's law. And lastly, Stefan-Boltzmann law states that the emissive power of a black body is directly proportional to the fourth power of its absolute temperature. So if emissive power is Q and absolute temperature is capital T, T to the power Q varies as T to the power 4. Then proportionality constant term, epsilon emissivity, which is a surface property. Epsilon is equal to 1 for a black body. Sigma is the Stefan-Boltzmann constant. It is always 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. And Ts is the absolute temperature of the surface. Now this is the analogy for electrical circuit T1, T2 and Q. And the resistance is 1 by this whole term. So we have what we have learned? We have learned that there are three modes of heat transfer: conduction, convection, and radiation. For convection, this is governed by the intermolecular interactions, and it is governed the law which governs the conduction is real law of heat conduction. The rate of heat flow through a simple usually directly proportional to the area of the section at right angle, that is here Q. The section at right angle is A. Direction of difference change of temperature and change of temperature with respect to the length. Change of temperature with respect to the length. So Q varies as A dt dx. So constant term minus K. K is the thermal conductivity, unit is watt per meter Kelvin. Now thermal resistance, current is equal to from Ohm law. Potential to electric resistance for, if we apply the same concept for conduction, it is Q varies dt dx by k. This comes from here. Now convection requires intermolecular interactions and bulk transport. So convection needs fluid matter. So from Newton law of cooling, Q is equal to H As. Q is equal to H As. Ts minus T. Ts is the temperature of the solid. Tf is the temperature of the fluid. And H is the heat transfer coefficient. Unit is watt per meter square Kelvin. And radiation is the transfer of heat by electromagnetic radiation, where there is no medium. That arises due to temperature of the body. Radiation does not need matter. Between sun and earth, there is no matter to transfer the heat. Here in my first lecture.